Okay, the second law of thermodynamics. There are limits to the efficiency of heat engines. The ideal engine would convert all input energy into useful work, but it turns out that such an engine is impossible to construct. The Kelvin-Planck formulation of the second law of thermodynamics can be stated as no heat engine operating in a cycle can absorb energy from a reservoir and use it entirely for the performance of an equal amount of work. This form of the second law means that the efficiency of engines must always be less than 1. So you can see in the equation here, some energy must always be lost to the environment. In other words, it's theoretically impossible to construct a heat engine with an efficiency of 100%. To summarize, the first law says we can't get a greater amount of energy out of a cyclic process than we put in. And then the second law says we can't break even. No matter what engine is used, some energy must be lost. Sorry for the interruption there. I don't know if you're seeing that or not. No matter what engine is used, some energy must be transferred by heat to the cold reservoir. There's another equivalent statement of the second law. If two systems are in thermal contact, net thermal energy transfers spontaneously by heat from the hotter system to the colder system. Here, spontaneous means the energy transfer occurs naturally with no work being done. Thermal energy naturally transfers from hotter systems to colder systems. That means work must be done to transfer thermal energy from a colder system to a hotter system. An example is the refrigerator, which transfers thermal energy from inside the refrigerator to the warmer kitchen. We just saw that no engine can operate with 100% efficiency, but different designs yield different efficiencies. And it turns out that one design in particular delivers the maximum possible efficiency. This design is the Carnot cycle, which we will discuss in greater detail in a few minutes. Understanding the Carnot cycle requires the concepts of reversible and irreversible processes. In a reversible process, every state along the path is an equilibrium state, so the system can return to its initial conditions by going along the same path in the reverse direction. A process that doesn't satisfy this requirement is irreversible. Most natural processes are known to be irreversible. The reversible process is an idealization. Although real processes are always irreversible, some are almost reversible. If a real process occurs so slowly that the system is virtually always in equilibrium, the process can be considered reversible. Imagine compressing a gas very slowly by dropping grains of sand onto a frictionless piston, as in the figure here. The temperature can be kept constant by placing the gas in thermal contact with an energy reservoir. The pressure, volume, and temperature of the gas are well defined during this isothermal compression. Each added grain of sand represents a change to a new equilibrium state. This process can be reversed by slowly removing grains of sand from the piston. It's Nana and Papa. I don't know. I don't have my. We just had a new grandbaby, so we're getting interrupted with pictures of the grandbaby. Sorry about that. In 1824, I have to go to the Carnot Engine. I apologize. In 1824, a French engineer named Sadi Carnot, who lived from 1796 to 1832, described a theoretical engine now called a Carnot engine that is of great importance from both a practical and a theoretical viewpoint. He showed that a heat engine operating in an ideal reversible cycle now called the Carnot cycle, between two energy reservoirs is the most efficient engine possible. This establishes an upper limit on the efficiencies of all real engines. Carnot's theorem tells us that no real engine operating between two energy reservoirs can be more efficient than a Carnot engine operating between the same two reservoirs. In a Carnot cycle, an ideal gas is contained in the cylinder with a movable piston at one end. The temperature of the gas varies between Tc and Th, that is temperature cold and temperature hot. The cylinder walls and the piston are thermally non-conducting. The figure shows the four stages of the Carnot cycle. Let's go over each stage. The cycle consists of two adiabatic and two isothermal processes, all reversible. The process A to B, shown in figure A, is an isothermal expansion at temperature TH, in which the gas is placed in thermal contact with a hot reservoir, a large oven, for example, at temperature TH. During the process, the gas absorbs energy QH from the reservoir and does work WAB in raising the piston. In the process B to C, figure B, the base of the cylinder is replaced by a thermally non-conducting wall, and the gas expands adiabatically, so no energy enters or leaves the system by heat. During the process, the temperature falls from TH to TC, and the gas does work WBC in raising the piston. In the process C to D, figure C, the gas is placed in thermal contact with a cold reservoir at temperature Tc and is compressed isothermally at temperature Tc. During this time, the gas expels energy Qc to the reservoir, and the work done on the gas is WCD. In the final process, D to A, figure D, the base of the cylinder is again replaced by a thermally conducting wall, and the gas is compressed adiabatically. The temperature of the gas increases to TH, and the work done on the gas is WDA. The PV diagram for the Carnot cycle is presented in this figure. The net work done, WENG, equals the net energy transferred into the Carnot engine in one cycle, the absolute value of QH minus the absolute value of QC. For a Carnot engine, we have the relationship shown, which relates the thermal energy transfers and the absolute temperatures. Let's substitute this relationship into our equation for efficiency. We find the thermal energy of a Carnot engine, where T must be in kelvins. From this result, we see that all Carnot engines operating reversibly between the same two temperatures have the same efficiency. This equation can be applied to any working substance operating in a Carnot cycle between the two energy reservoirs. According to this equation, the efficiency is 0 if Tc equals Th. The efficiency increases as Tc is lowered and as Tc is increased. The efficiency can be 1 only if Tc equals 0 Kelvin. According to the third law of thermodynamics, it's impossible to lower the temperature of a system to absolute 0 in a finite number of steps. So such reservoirs are not available, and the maximum efficiency is always less than 1. In most practical cases, the cold reservoir is near room temperature, about 300 K. So increasing the efficiency requires raising the temperature of the hot reservoir. All real engines operate irreversibly due to friction and the brevity of their cycles, and are therefore less efficient than the Carnot cycle. And with that, we'll stop. The next subject we're going to talk about is entropy. Where's my mouse?